Good afternoon, everyone. This is Tom Cherry Holmes, and this is another video in the Retro Computing Archaeology series, a series of videos intended to shed light on a variety of retro computing subjects. And in this video, we're going to be talking about what was recently put up and published, which were the atari-coin-op game development tools, notably the assembler and the linker. We are going to go through the entire process of taking the original source code from Centipede, making a change to that source code, and assembling and linking all the way through to the process of creating ROMs that can be put into our ersatz development system. Before I continue, I wanted to make a formal apology for the previous video because a certain video conferencing software that rhymes with shroom had decided to mess with my audio settings. With that out of the way, let's begin. The goal here, as I stated before, is to demonstrate atari-coin-op's 6502 macro assembler for PDP-11 in context. For a little bit of what this is, these are the development tools that the atari-coin-op developers used from about 1976 until the early 1980s, when it was ported over to C to develop coin-op games. What we won't be showing here are the graphic tools because, well, there really weren't any. Well, not very many, and not what you would consider to be graphic tools. I mean, mostly what was used was graph paper. But with that, we're going to be demonstrating this inside of a simulated PDP-11 machine. And what we're going to be demonstrating is essentially, to explain what happened here, a developer, Dave Shepard, took PDP Macro 11, which was Digital Equipment Corporation's macro assembler for the PDP-11, and he transmogrified it, that is, severely modified it, to, instead of emitting PDP-11 machine code, it emitted code for either 6502, 6800, or 6809 CPUs. And even more were added later when they took and they transitioned that over to C. But we're going to be showing just the modified Macro 11 version here. To do that, we're going to be giving a quick overview of the PDP-11 development system that's being used here in simulation. And to do this demonstration, we're going to be modifying an original Centipede coin-op source code. We're going to be assembling that source code, linking that source code to create an absolute binary because the assembler outputs object files. And then we're going to take that absolute binary and cut it up into ROMs that we can take via paper tape and send over to our development system that's running MAME. So with that, let's get started. We'll talk a little bit about what are we trying to target here. Well, this is Centipede, and if we look at the board for Centipede, this is a custom computer, as was the practice for arcade game coin-op designers at the time. They would build a specific computer to run this game, and it would have just the logic needed to do all of the various different things like all of the movable objects, which are the enemies, handle the playfield logic, the tiles for the playfield and whatnot, in this case, the mushrooms, etc. And it would have the necessary CPU, in this case, a 6502, and any I/O chips, such as a PIA for talking to the outside world, and have the various connectors, as you can see, to take and talk to the joysticks, the monitor, all of the controls, the buttons, etc. What we're actually going to be modifying here corresponds exactly to these four EPROM chips down here at the bottom of the board and these two EPROM chips here at the center of the board. Okay, a little bit about what we're going to be modifying here. This is Centipede. It was developed by Ed Logg and Donna Bailey throughout 1980, and the first version of Centipede was released in March of 1981. What we're actually going to be modifying here is revision 2 that was actually put into production May 28th of 1981 here, and it's based on the 6502 CPU. A little bit about our development system here. Now you'll notice that we've got this board over here, but there's not really any input and output for a keyboard or disk or storage device. So how are we going to take and develop the code here? Well, it turns out we need a bigger computer, first of all, that can handle it. We need a machine that can handle more memory than is configured for this guy right here. You know, you only have a few kilobytes of RAM, and it's mostly ROM over here. You're not going to be able to fit your program source code into that. So you need to have a much larger computer, like one of these. A PDP-1123 in this case, from 1979. The central processing unit is actually this little bit right here in the middle, and the bits of the cabinet directly underneath it. Up here on top, we actually have a DEC RX02 floppy drive here. We're actually going to be using RX01s here, but these are floppy drives, 8-inch floppy drives. And you've got some large-scale storage here to hold the operating system and potentially data files for daily use here. You see right here, it's the RL02 10 megabyte disk pack in this picture here, but for our purposes, what we're going to be using are a set of 3 RK05 2.5 megabyte disk packs here. These were extremely common back in the mid to late 70s and up into the early 80s here. They used cartridge platters here that were originally based on the IBM 2315 disk pack platter and popularized by Diablo as the Model 31 disk drive. And each of these basically hold about 2.5 megabytes of information. You can see this one right here in the cabinet right here is the RT11 version 4 boot for the 1134 that this thing is presumably attached to. Usually this is directly inside the cabinet. You'll see all sorts of little buttons here so that you can turn it on, take and set it to make sure that it's set to ready, set write protect so you don't accidentally write stuff to it. Once you've loaded a cartridge, you need to press the load switch to make sure that it gets mounted, etc. And that's all this stuff right here. Plus you've got a little indicator here indicating which particular RK05 drive this actually is. We're going to be using 3 of them. So we also have for data backup and stuff, because you really can't put an RK05 disk pack in your pocket. And I can argue that you can't really put an 8-inch disk in your pocket either. We've got 2 floppy drives here. This is the digital RX01 or DEC RX01. These format standard IBM 3740 floppy disks, 8 inches. 256 kilobytes of capacity, and fairly easy to read, not only on these particular drives, but on other systems as well. So we're also going to need a way to get data out, because we're not going to be able to take this RX01 floppy and bring it over to our development system to read it. It accepts paper tape. So we're going to need a paper tape reader and a punch. So we're going to be using a DEC PC05 as the paper tape punch here. So we have right here, this device right here in the middle is the reader, and it basically takes a stack of paper tape, which is literally paper that has whole bunches of little holes punched in it, 1 line for each binary byte with 8 little holes plus a sprocket hole right in the middle of it to keep everything in line. And it's just have a little optical reader in the middle here that's basically looking at the holes and turning those into binary digits and bytes to go right down the line to the controller. In addition to the reader here, the right-hand side that you can't see very well is actually the punch. So this is how we create the tapes. We read the tapes over here, but we create the tapes over here on this little pocket on the right. And actually, in the back of this unit, there's actually a bin. There's actually a bin to hold the fan-folded paper tape that DEC like to use. You can get it ready, put it ready, and put it into the punch, so that when you're ready, you just push the button on the punch to take and spit out some leader. And then when you do program control from RT11, you spit out your paper tape, and there it is. There's also a little bin inside here to take and hold the little chads that get punched out when they punch through the paper. So, but we need a way for a programmer to interact with the computer itself, because if you recall here in this earlier picture, there's not really a console here. It's just kind of these stacks of racks of equipment right here. So we need some sort of display and keyboard that we can use to talk to the machine, and that's a terminal. And during the late 70s to early 80s, the most popular terminals to use were the DEC VT52, and we're actually going to go up one here and use a DEC VT100. This is the terminal that is the daddy of basically all Xterms and console windows, etc., that we use in operating systems like Linux today. All descend from this guy. 80 characters by 24 lines. And lots of control character sequences to do full screen types of things, which we're going to be using with the KED editor a bit later. So here is our console, and this is connected directly to the console port at the back of the 1123 in our case. And we're going to be using an operating system called RT11. RT11 is a very simple operating system. You can actually see a screenshot of it right here on the screen doing a directory. It is a single tasking, single job operating system, and you can think of it directly. The direct analog would be something like MS-DOS today, or a bit older CP/M. Took a lot of inspiration from this particular operating system and its close cousins like OS 8, also from DEC and others. RT11 only allows you to do one thing at a time here, but that's okay because right now we're a single developer using a single console here, and it'll be great for our purposes. Now, a little overview. We're just going to need, we will need some sort of a black box connected to our arcade hardware so that we can test the code that we have written, okay? And for this, we have a board that's basically going to be putting its little tentacles into the CPU socket and intercepting all of those signals to go out to something like a logic analyzer to take and debug it. Well, we don't have a logic analyzer here, so we're going to be using the MAME. We're going to be using the MAME emulator and its debugger to take the place of the HP 1611A logic analyzer here. And we're going to be taking the input from the paper tape that we've done on our PDP-11 here to take and create our EPROMs that we can take and then stuff into the board for testing. And I'm going to take and talk out this parenthetical here, using paper tape as an example of the improvisation needed by old school developers to get artifacts to their destination, and is not indicative of the exact process used at Atari. Okay, good. Glad you're with me on that. So the first thing we got to do, we need to take and edit some code, all right? So for that, we need to actually take and boot into RT11. And for that, I've got a special window over here specifically for that purpose. And I have a special little GitHub repo, which I have in the description here, so that you can use to follow along here. It has all of the tools from the coin-op tool set. It has a copy of Centipede along with its original production binaries here that you can use for reference. We use this to basically debug the tools to make them work for this demonstration. And we have a reassembled copy here that we were basically diffing back and forth to make sure that what we got matched up exactly. We also have a folder here called Coin-op, which is our SimH installation here, and we can use this to boot into RT11 to do our demonstration. And of course, all of the notes for my talk here, including this org file that you're seeing over here in Emacs, is here in the org talk directory here. So all you guys can follow along. So with that, let's go ahead and start. We'll go into Coin-op here, and if we look inside of here, we've got a set of disk images for everything that we need. We have a disk image for our system drive, for our code and object drive, and for our final binaries here. So we've got three RKO5s, and we've got some RX01 disks that I was used during the process of building all of this stuff. These are floppies that you can mount to, whatever you wish to do. And we have a file called coin-op here, which basically just sets up the system to something that matches the reality that we need here. I'm not throttling anything because I don't want to have you guys basically just wait here to empty space while this thing pretends to be slower than it actually is. We're going to be running this at the full speed of my computer, which means that the assemblies and links are going to be pretty much instantaneous. So it sets everything up and then it immediately takes and boots RK0 here. So if we run our emulator with the configuration file, we will find ourselves immediately sitting inside of RT11. And yes, I did bounce all the way to version 4 here because it turns out I really like the keypad editor KED. I didn't think bouncing around in T-code would be very visually appealing. So now, one thing that did happen here, we did not use ODT at all, the online debugging tool, which is the tool that you see for the front panel on devices like this right here, which is used to boot the system. So we bypassed ODT entirely and its boot prompt to go directly into RT11 here. And that's one small difference that I feel that I will need to point out because ultimately somebody else will point it out before I do. Okay. We sit here and now we are at what is called the dot prompt for RT11 here. And it's waiting for a command for us to do something. We can, of course, take and do certain commands. We can always, we have online help. So you have the ability to take and get online help for a number of different commands, like say the directory command. And so on. Boom, boom, boom. So yeah, it came with its own little bits of online help, which was very helpful. But in our case, I'm going to take a quick little look around the file system to show what we have here. If we do a directory right now, DK is pointed at the system drive. DK is the default disk volume. And we see basically, and yes, I'm going to cheat here a little bit. We've got some scroll back. We don't have this on a real VT100 terminal. This is one reason why a lot of system consoles back in the day actually used teleprinter terminals instead of glass terminals. So we have basically a directory of the system disk with all the system files, where these are device drivers and some basic utilities and things that we need, like pip for copying files. We have the keyboard editor here, which we're going to be using a bit later, the PDP-11 macro assembler, and so on. If we actually scroll all the way down to the bottom, we see some source code for the various drivers and things. And this was actually important because DEC actually provided source code for all the various bits of all of their utilities and device drivers and things, because the people who were buying these computers were using them for real computing tasks and they needed to get stuff done. And sometimes that meant modifying system tools to do what you need to do, which is what happened here. The developers at Atari basically took macro and turned it into Mac65 for 6502 CPUs, Mac68 for 6800 CPUs, and the linker was turned into a linker for microcomputers, LinkN, which we'll be using here. Great. So we also have DK1, which contains our source code right here, as well as a command file for building all the bits and pieces together. And if we actually take a look, sorry. One thing that you'll notice here is that as I hit the backspace key, because RT11 might be outputting to a teleprinter terminal, it implements rub out in a way that when you press the delete key, it shows you the character that it just deleted, so it does it backwards. An interesting little side effect here. We'll put in the drive specification so it knows that we're talking to drive 1 here. And we'll do a little type here. So we've now displayed the contents of this particular file, and inside this file, We have a few assignment commands to map the RK1 drive so that the assembler knows where things are. We're going to do this a little bit differently. And then we immediately take and we use the run command here to call Max65 to do the assembly, do linkm to do the link, and then we use a tool called image file to take and split all of this up. So this is essentially what we will be doing by hand to demonstrate the process, but it's here just nonetheless. So with that out of the way, I'm going to do one small thing here to make things a bit easier to deal with, and I'm going to use the assign command to say that I want the default drive to be RK1 here, or DK1. That will make the commands that I need to type much easier. So now when I do a directory, instead of seeing the system drive, DK is now pointed to RK1 for me automatically. With that, now we can immediately go in to start with step 1 here of the process, which we're going to edit the code to do our change. To do that, we're going to use the edit command, and we're going to use the KED version of the editor. This is the keypad editor. It's a full screen editor. And we're going to edit the file SimIR2, which contains the IRQ handler, but it also contains the various messages used for various displayed strings inside Centipede itself. And once we do that, we'll see that the screen has now changed, and we have the source code for this part of Centipede up on screen here. We can move around, we can scroll up, we can scroll down, and you can see certain things like assembler directives for setting page titles for printed listings, including files, etc. We start off here with basically what is over here on the left-hand column is a label. And the way that you do assembler files is that you typically have label, then you have some sort of opcode or directive, and then you have parameters. And then anything after that is basically these semicolons here are comments. We're going to scroll all the way down. We've got a macro here that's defined called ASCII in to basically make it easier to specify where in display memory we want this particular string to be displayed and what to be displayed. In our case, we're going to modify the high scores. We're going to modify the high scores header at the top of the page here to say something else. So we will move our cursor over. We'll hit the delete key to take and delete the old message here, and then we'll write in our new message. There we go. Now we've made our edit, and at this point, I now need to use some special keys that don't exist on a PC keyboard. So I have to enter their escape sequences by hand. First, I need to take, and you can see the escape sequences that I need to enter over here on the left-hand side. So first, I need to take and emit a PF1. Then I need to emit a 7 on the keypad, which will put us into command mode. And then I need to issue the command exit. Exit will save the file and return back to the RT11 dot prompt. But first, I need to take and confirm this command with a enter on the keypad, not on the main keyboard, but on the keypad. To do that, with that escape key, escape OM, and we find ourselves immediately back at the dot prompt. We have now completed first step here, modifying our code. And now we can immediately go on to start to assemble the code. We need to turn this code into machine code, or into object code. But this actually needs to happen in two passes here. The macro assembler will assemble the code, but it won't assemble it to specific places in memory, so things like jump addresses and stuff won't have absolute addresses and stuff. So we can't just take the things that come out of Mac and put them directly onto an EPROM. But we do need to do the first part of the assembly here. To do that, we'll use the run command. And again, window focus, fellas. Okay, there we go. So we run max65. We can see once we've done this that the prompt changes to an asterisk, indicating that we're now running max65 and it's waiting for a command. In this case, it's called a CSI directive that basically says, okay, give me the destination file and then give me the source files that make up that destination file. In this case, the destination file is an object file and the source files are the Mac files that we need to assemble. If you recall from the earlier directory listing, there are several files that we actually need to do here. So we need to first assemble the main part of the program. And we can actually do this in any order. We're just assembling these files here. First the main loop, then the IRQ handler. Sorry. Then the test routines, then the sync prom. So all of those pretty much assembled instantaneously. In real life, it would not be anywhere near that fast, but we're doing this fast for the sake of demonstration. We also, there's one that needs to be put here, and I'll go ahead and put it here. I need to do sendpick as well. So now we've assembled those files, and we can hit Control-C on our keyboard to abort max65 and come back to the dot prompt monitor. And yes, another word for the part of the system that we're in right now is the KMON, or the keyboard monitor, in case someone decides to point that out. So now, in addition to the Mac files that we have here on DK1 now, we also have the backup for the old version of our CentIR2 file that we changed, but we also have here a series of relocatable object files. These need to be combined together and have all of their symbols resolved and everything laid out absolutely in memory as an absolute memory file. And to do that, we need to use the linker. And as we had a special version of macro to assemble the 6502 code, so we also have a special version of link called linkm for link for microcomputers to take and generate our output files. And for that, it's the same thing. We just are linkm. We can do this because both max65 and linkm, as I showed before, are on the system drive, so I can just refer to them and it will take and load them up. And then we can immediately take and do our link. Now, the format of this link here is, again, the destination. Sorry, let me do that. I accidentally brought the asterisk along with me because I'm an idiot. Yes, no input. Yes, thank you for pointing that out because I rubbed over it. But we have a destination, of course. We have a destination save file followed by a memory map file so we can see where everything was placed in memory. It's just a text file that we can reference. Equals, and that separates the destination from the source. And they need to be made up of Centi2, CentIR2, and CentTS2 object files. We do not need to put their extensions because linkm just assumes that's what we need to use. And since there were no errors and the link was very straightforward, it simply brought us back to the prompt for the next one. Sendpick and our sync. So there we go. We can now hit Control-C, find ourselves back at the monitor at the dot prompt. And now we can see that no new files have shown up on DK1. However, if we look on DK2, we will see that we now have two types of files. I'm going to go ahead and assign. Sorry. Okay. Never mind. Doesn't matter. Okay. We're going to see that there are two types of files here. We have our save files. These are the files that we're going to take and ultimately cut up into our EPROMs. And we've got map files. The most useful one of the map files is Centipede. And if we take a look at it, we can see that this is output from Atari Link-M version 4.6. This is the load map, and where everything is placed inside the file and in memory as a result. Starting at address 0 is 3366 hex bytes, and then each of these entries are the global symbols that are found in the file and where they are placed. Of special note, there are some interesting ones here. The most important ones, ironically, are the reset vector. That needs to be in the right place or the game won't work at all. The RQ handler here, hex 3879. But you see these these checksum symbols. These are variables that are kept in memory and that are calculated for various parts of the code, mostly strings, the most important one being the Atari copyright string. So if you just had a hex editor and you wanted to just change the copyright string on the main attract mode screen here and you changed it, what you would find is that the game would no longer work because the checksum calculations would no longer match up and it would immediately jump through the watchdog timer handler to crash the machine. Boom. Anyway, with that little digression aside, we can now basically move on. Now we need to take and send these files to our black box via paper tape. And we've got 3 files that we need to send here. Our picture data, our sync prom, but also the main part of our program code right here. And these are 512-byte blocks, by the way. 512-byte blocks, by the way. So, okay, great. So we got that. How are we going to send that over? Well, we need to use the paper tape punch for that. And in order to do that, I actually need to ready the paper tape punch. I will stop the simulation by hitting Control E, and then I will attach to the paper tape a new file called centipede.save right here. And then I will continue the simulation and we'll be back where we were. And we're actually sitting at a dot prompt here. If I hit the return key, you'll see it take and emit another one. I need to take and send this file over to paper tape punch. And in reality, this will take a few minutes. But we wind up with a nice big pile of paper tape that we can now feed into the development system here. And we need to do it for the other 2 files. So again, Control E, ETP. We'll do sendpick next. Do it one more time for the sync prom. So there we go. Those 3 files are now, we have a nice big pile of paper tape ready to get over to our development box. Okay. We then take and read it in. So now that we've got this in, we're done with RT11 here, and we can basically quit RT11 completely. And we do this literally by stopping the machine. There is no shutdown procedure. We can literally just turn the damn thing off. And now we're sitting back here on our development system, and we have our 3 artifacts. And if we take a look at each of these, we'll see that each of these is an absolute memory image containing exactly the output from the assembler, assembled at the right address with all the addresses pointing to the right place. We have 4K of picture data. we have 16 kilobytes worth of EPROM data. However, if you notice, the first 8 kilobytes of this particular image is blank. And that's because the assembly orgs literally starts at 2000. And then the rest of the code is just immediately one right after that. So we need to take and split this all up into separate 2 kilobyte EPROMs. There's an 8K gap at the beginning that we need to take and skip. Now, normally we would be using a program called image file on the RT11 to actually do this for us. Well, we don't have that, so we have to take and replicate that using DD under Linux. And I happen to have all the commands that we need in order to do that. So all we really need to do is use DD to split all these up into their requisite places. We'll see each one of them here. So this is the first DD command, which gets the first 2 kilobytes of program data. It comes from Centipede save. It outputs directly to the main development system with the right prom number in the right location on the board. And to make things easy, I set the byte size to 2048 bytes, and we skip the first 8192 bytes here. Boom, there's our first file. Our second file. Third file. And here's the last bit of the code. So the code is split up into those 4 EPROMs that you saw down at the bottom of the board. Those are now in, and they're inserted into the board at the moment. But we also need to do the 2 picture proms. These are a lot more straightforward. There's no blank space at the beginning, so there's no skip, so we just take and slice them up appropriately. And we also need to do the sync prom. This is a teeny tiny little bipolar prom here that's used as a finite state machine for the IRQ handler, among other things. If you ever wonder where, did Steve Wozniak come up with the idea of using a prom as a state machine for the Disk2 sequencer? No, he did not pull that out of thin air. Coin-op guys at Atari were doing it before he did. Let's just put that there. So there's our sync here, and we're only needing the first 256 bytes of this sync prom right here. It actually output a much larger file. So we just take that, snap that out, there's our sync prom, everything's good. And at that point, we're done. We've now put it into the development system, and we can immediately take and go over to our development system. We're walking over to our development system here. And loading the debugger. And now we're sitting here looking at the debug window here. For Centipede, the system hasn't started yet. It's sitting here literally at the reset vector, ready to go the moment that I take and press the run button here. But we can see, just like on the logic analyzer, you will have an instruction trace, and you'll have a little look into some of the states of the processor, etc. Here we have it where we can show the state of the processor and what it's actually assembling, etc. So now I can basically take and go over here, hit the run button, and let's see if it works. Ooh, looks like we got a display. And there it is, right there. We have our Hello World display. Our modification was successful and everything was assembled, and we wound up with a workable binary here. So there we go. That is now really officially the end of my little video here. As I leave here, I can't help but point out, I've copied this into the description of the video here, but the references for everything that I've used here include the atari-coin-op-assembler repo, which has all these bits and pieces that were used in this demonstration, so you can do this yourself. You can mess around with it. Maybe you can try some of the other games that are present in the historical source repo over here on GitHub. I would like to thank the proprietor of Historical Source for making all of this available. Jason, you are doing God's work, man. Okay, the atari-coin-op tools were originally pulled from a wonderful site called Bitsavers.org. It's run by the excellent Al Kossow, former Apple engineer, former Silicon Valley engineer. Basically, legend, has been collecting all of this stuff for us to take and for all of the, just as one big library and one big reference. You can't live without it if you're doing this archaeology stuff. And finally, I want to thank Jim Geist here for helping me solve the last leg of this. Basically, when we put everything together and got it working, we're finding that the linker on disk F8 was not producing binaries that matched up with production for one reason or another, and it turned out that the linker that's on disk F8 wasn't the right one. And he happened to notice that the source code to linkem, which I couldn't find because the file name was different, was actually on disk E2 as link0.mac. And so we were able to take and rebuild it, put everything together. He was able to test and verify that the binaries matched, and I was able to reproduce. So we were able now to do this demonstration, which hopefully at VCF East this year, I will actually be demonstrating this by plugging it into a real Centipede board. Stay tuned. Finally, again, I want to thank Historical Source here, the one, the only, Jason Scott and his archive team at the Internet Archive for putting up a GitHub repository full of all of this code, including tons and tons of atari-coin-op games. This is one other big reason why this is even possible in the first place. Thank you so much for that. So I'll leave the video here, guys. I hope you guys enjoyed it. If you have any questions, feel free to leave comments. Hopefully the audio is better this time. If there are issues, please let me know and I'll record it again. Oh, God. Yeah. Until next time, guys. Have fun.